In the last episode, I read the first 10 pages of the book, The Beginning of Infinity, and I also discussed about what I learned. And today, I'm going to continue from where I left that day. So it is page 11 now. So listen carefully and enjoy learning with me. And also, if you have any questions and would like to discuss about any topics, please write your comment below. Okay, so this page starts with this sentence. I am not asking what authority scientific knowledge is derived from or rests on. I mean, literally, by what process do ever truer or more detailed explanations about the world come to be represented physically in our brains? How do we come to know about the interactions of subatomic particles during transmutation at the center of a distant star? When even the tiny trickle of light that reaches our instruments from the star was emitted by glowing gas at the star's surface, a million kilometers above where the transmutation is happening. Or about conditions in the fireball during the first few seconds after the Big Bang, which would instantly have destroyed and scientist and sentient being or scientific instrument. Or about the future, which we have no way of measuring at all. How is it that we can predict with some non-negligible degree of confidence whether a new design of microchip will work or whether a new drug will cure a particular disease, even though they have never existed before? This is a good question. I like this question. For most of human history, we did not know how to do any of this. People were not designing microchips or medications or even the wheel. For thousands of generations, our ancestors looked up at the night sky and wondered what stars are, what they are made of, what makes them shine, what their relationship is with each other and with us, which was exactly the right thing to wonder about. And they were using eyes and brains anatomically indistinguishable from those of modern astronomers. But they discovered nothing about it. Much the same was true in every other field of knowledge. It was not for lack of trying, nor for lack of thinking. People observed the world, they tried to understand it, but almost entirely in vain. Occasionally, they recognized simple patterns in the appearances, but when they tried to find out what was really there behind those appearances, they failed almost completely. I expect that, like today, most people wondered about such things only occasionally during breaks from addressing their more parochial concerns, but their parochial concerns also involved yearning to know, and not only out of pure curiosity. They wished they knew how to safeguard their food supply, how they could rest when tired without risking starvation, how they could be warmer, cooler, safer, in less pain in every aspect of their lives. They wished they knew how to make progress, but on the time scale of individual lifetimes, they almost never made any. Discoveries such as fire, clothing, stone, tools, bronze, and so on happened so rapidly that from an individual's point of view, the world never improved. Sometimes people even realized with somewhat miraculous prescience that making progress in practical ways would depend on progress in understanding puzzling phenomena in the sky. They even conjectured links between the two, such as myths, which they found compelling enough to dominate their lives, yet which still bore no resemblance to the truth. In short story, what happens is that they wanted to create knowledge. So yes, in short, they wanted to create knowledge in order to make progress, but they did not know how. This was the situation for our species earlier prehistory, through the dawn of civilization, and through its imperceptibly slow increase in sophistication, with many reverses until a few centuries ago, then a powerful new mode of discovery and explanation emerged. And can you guess what it was? Which later became known as science. Yes, it is science. Absolutely. Its emergence is known as the scientific revolution because it succeeded almost immediately in creating knowledge at a noticeable rate, which has increased ever since. What had changed? What made science effective at understanding the physical world when all previous ways had failed? What were people now doing for the first time that made the difference? This question began to be asked as soon as science began to be successful. And there have been many conflicting answers, some containing truth, but none, in my view, has reached the heart of the matter. To explain my own answer, I have to give a little context first. The scientific revolution was part of a wider intellectual revolution, the Enlightenment, which also brought progress in other fields, especially moral and political philosophy, and in the institutions of society. Unfortunately, the term the Enlightenment is used by historians and philosophers to denote a variety of different trends, some of them violently opposed to each other. What I mean by it will emerge here as we go along. It is one of several aspects of the beginning of infinity and is a theme of this book. But one thing that all conceptions of the Enlightenment agree on is that it was a rebellion. Yes, it was a rebellion, and specifically a rebellion against authority in regard to knowledge. Rejecting authority in regard to knowledge was not just a matter of abstract analysis, it was a necessary condition for progress because before the Enlightenment, it was generally believed that everything important that was knowable had already been discovered and was enshrined in authoritative sources such as ancient writings and traditional assumptions. Some of those sources did contain some genuine knowledge, but it was entrenched in the form of dogmas along with many falsehoods. So the situation was that all the sources from which it was generally believed knowledge came actually knew very little. What? So the situation was that all the sources from which it was generally believed knowledge came actually knew very little and were mistaken about most of the things that they claimed to know. And therefore, progress depended on learning how to reject their authority. This is why the Royal Society, one of the earliest scientific academies founded in London in 1660, took as its motto nullius in verba, which means something like take no one's word for it. However, Rebellion against authority cannot by itself be what made the difference. Authorities have been rejected many times in history, and only rarely has any lasting good come of it. The usual sequel has merely been that new authorities replaced the old. What was needed for the sustained, rapid growth of knowledge was a tradition of criticism. Before of enlightenment, that was a very rare sort of tradition. Usually, the whole point of a tradition was to keep things the same. Thus, the Enlightenment was a revolution in how people sought knowledge. By trying not to rely on authority, that is the context in which empiricism, purporting to rely solely on the senses of knowledge, played such a salutary historical role, despite being fundamentally false and even authoritative in its conception of how science works. One consequence of this tradition of criticism was the emergence of a methodological rule that a scientific theory must be testable, though this was not made explicit at first. That is to say, the theory must make predictions which, if the theory were false, could be contradicted by the outcome of some possible observation. Thus, although scientific theories are not derived from experience, they can be tested by experience, by observation or experiment. For example, before the discovery of radioactivity, chemists had believed and had verified in countless experiments that transmutation is impossible. Rutherford and Soddy boldly conjectured that uranium spontaneously transmutes into other elements. Then, by demonstrating the creation of the element radium in a sealed container of uranium, they refuted the prevailing theory and science progressed. They were able to do that because that earlier theory was testable. It was possible to test for the presence of radium. In contrast, the ancient theory that all matter is composed of combinations of the elements earth, air, fire, and water was untestable because it did not include any way of testing for the presence of those components. So it could never be refuted by experiment, hence it could never be and never was improved upon through experiment. Wow, this is amazing. The Enlightenment was at root a philosophical change. The physicist Galileo Galilei was perhaps the first to understand the importance of experimental tests, which he called sementi, meaning trials by ordeal, as distinct from other forms of experiment and observation, which can more easily be mistaken for reading from the book of nature. Testability is now generally accepted as the defining characteristic of the scientific method. Popper called it the criterion of demarcation. Criterion of demarcation between science and non-science. Nevertheless, testability cannot have been the decisive factor in the scientific revolution either. Contrary to what is often said, testable predictions had always been quite common. Every traditional rule of thumb for making a flint blade or a campfire is testable. Every would-be prophet who claims that the sun will go out next Tuesday has a testable theory. So does every gambler who has a hunch that this is my lucky night, I can feel it? So what is the vital, progress enabling ingredient that is present in science, but absent from the testable theories of the prophet and the gambler? The reason that testability is not enough is that prediction is not and cannot be the purpose of science. Consider an audience watching a conjecturing trick. The problem facing them has much the same logic as a scientific problem. Although in nature there is no conjurer trying to deceive us intentionally, we can be mystified in both cases for essentially the same reason. Appearances are not self-explanatory. If the explanation of a conjuring trick were evident in its appearance, there would be no trick. If the explanations of physical phenomena were evident in their appearance, empiricism would be true, and there would be no need for science as we know it. The problem is not to predict the trick's appearance. I may, for instance, predict that if a conjurer seems to place various balls under various cups, those cups will later appear to be empty. And I may predict that if the conjurer appears to saw someone in half, that person will later appear on stage unharmed. Those are testable predictions. I may experience many conjuring shows and see my predictions vindicated every time. But that does not even address, let alone solve, the problem of how the trick works. Solving it requires an explanation, a statement of the reality that accounts for the appearance. Some people may enjoy conjuring tricks without ever wanting to know how they work. Similarly, during the 20th century, most philosophers and many scientists took the view that science is incapable of discovering anything about reality. Starting from empiricism, they drew the inevitable conclusion, which would nevertheless have horrified the early empiricists, that science cannot validly do more than predict the outcomes of observations, and that it should never purport to describe the reality that brings those outcomes about. This is known as instrumentalism. It denies that what I have been calling explanation can exist at all. It is still very influential. In some fields, such as statistical analysis, the very word explanation has come to mean prediction, so that a mathematical formula is said to explain a set of experimental data. By reality is meant merely the observed data that the formula is supposed to approximate. That leaves no term for assertions about reality itself, except perhaps useful fiction. Instrumentalism is one of many ways of denying realism, the common sense and true doctrine that the physical world really exists and is accessible to rational inquiry. Once one has denied this, the logical implication is that all claims about reality are equivalent to myths, none of them being better than the others in any objective sense. That is relativism. The doctrine that statements in a given field cannot be objectively true or false. At most, they can be judged, so relative to some cultural or other arbitrary standard. Instrumentalism, even aside from the philosophical enormity of reducing science to a collection of statements about human experiences, does not make sense in its own terms. For there is no such thing as a purely predictive, explanation-less theory. One cannot make even the simplest prediction without invoking quite a sophisticated explanatory framework. For example, those predictions about conjuring tricks apply specifically to conjuring tricks. There is explanatory information, and it tells me, among other things, not to extrapolate the predictions to another type of situation. However successful they are at predicting conjuring tricks. So I know not to predict that shows in general are harmless to humans, and I continue to predict that if I were to place a ball under the cup, it really would go there and stay there. What a stupid analogy, huh? Yes, I think so. The concept of conjuring trick and of the distinction between it and other situations is familiar and problematic. So much so that it is easy to forget that it depends on substantive explanatory theories about all sorts of things, such as how our senses work, how solid matter and light behave, and also subtle cultural details. Knowledge that is both familiar and uncontroversial is background knowledge. I don't know how. A predictive theory whose explanatory content consists only of background knowledge is a rule of thumb, because we usually take background knowledge for granted. Rules of thumb may seem to be explanationless predictions, but there is always an illusion. There is always an explanation, yes, I agree, whether we know it or not, for why a rule of thumb works. Denying that some regularity in nature has an explanation is effectively the same as believing in the supernatural, saying, "That's not conjuring, it is actual magic." Also, there is always an explanation when a rule of thumb fails. For rules of thumb are always parochial. They hold only in a narrow range of familiar circumstances. So here you might be thinking, what is a rule of thumb? So let me explain it for you. A rule of thumb is a general guideline rather than a strict rule or an approximate measure or means of reckoning based on experience or common knowledge. So this is rule of thumb. They hold only in a narrow range of familiar circumstances. So if an unfamiliar feature were introduced into a cups and balls trick, the rule of thumb I stated might easily make a false prediction. For instance, I could not tell from the rule of thumb whether it would be possible to perform the trick with lighted candles instead of balls. If I had an explanation of how the trick worked, I could tell. Explanations are also essential for arriving at a rule of thumb in the first place. I could not have guessed those predictions about conjuring tricks without having a great deal of explanatory information in mind, even before any specific explanation of how the trick works. For instance, it is only in the light of explanations that I could have abstracted the concept of cups and balls from my experience of the trick rather than say red and blue, even if it so happens that the cups were red and the balls blue in every instance of the trick that I had witnessed. The essence of experimental testing is that there are at least two apparently viable theories known about the issue in question, making conflicting predictions that can be distinguished by the experiment. Just as conflicting predictions are the occasion for experiment and observation, so conflicting ideas in a broader sense are the occasion for all rational thought and inquiry. For example, if we are simply curious about something, it means that we believe that our existing ideas do not adequately capture our or explain it. So we have some criterion that our best existing explanation fails to meet. The criterion and the existing explanation are conflicting ideas. I shall call a situation in which we experience conflicting ideas a problem. The example of a conjuring trick illustrates how observations provide problems for science, dependent as always on prior explanatory theories. For the conjuring trick is a trick only if it makes us think that something happened that cannot happen. Both halves of that proposition depend on our bringing quite a rich set of explanatory theories to the experience. That is why a trick that mystifies an adult may be uninteresting to a young child who has not yet learned to have the expectations on which the trick relies. Even those members of the audience who are incurious about how the trick works can detect that it is a trick only because of the explanatory theories that they brought with them into the auditorium. Solving a problem means creating an explanation that does not have the conflict. Similarly, no one would have wondered what stars are if there had not been existing explanations that unsupported things fall and that lights need fuel, which runs out, and so on, which conflicted with interpretations, which are also explanations of what was seen, such as that the stars shine constantly and do not fall. In this case, it was those interpretations that were false. Stars are indeed in free fall and do not need fuel. But it took a great deal of conjecture, criticism, and testing to discover how that can be. A problem can also arise purely theoretically without any observations. For instance, there is a problem when a theory makes a prediction that we did not expect. Expectations are theories too. Similarly, it is a problem when the way things are, according to our best explanation, is not the way they should be, that is, according to our current criterion of how they should be. This covers the whole range of ordinary meanings of the word problem, from unpleasant as when the Apollo 13 mission reported, "Houston, we have had a problem here," to pleasant as when Popper wrote. I think that there is only one way to science, or to philosophy for that matter, to meet a problem, to see its beauty and fall in love with it, to get married to it and to live with it happily, till death do ye part. Unless you should meet another and even more fascinating problem, or unless indeed you should obtain a solution. But even if you do obtain a solution, you may then discover to your delight the existence of a whole family of enchanting, though perhaps difficult problem children. Realism and the Aim of Science, 1983. Experimental testing involves many prior explanations in addition to the ones being tested, such as theories of how measuring instruments work. The refutation or refutation of a scientific theory has, from the point of view of someone who expected it to be true, the same logic as a conjuring trick, the only difference being that a conjurer does not normally have access to unknown laws of nature to make a trick work. Since theories can contradict each other, but there are no contradictions in reality, every problem signals that our knowledge must be flawed or inadequate. Our misconception could be about the reality we are observing, or about how our perceptions are related to it, or both. For instance, a conjuring trick presents us with a problem only because we have misconceptions about what must be happening, which implies that the knowledge that we use to interpret what we are seeing is defective. To an expert steeped in conjuring lore, it may be obvious what is happening, even if the expert did not observe the trick at all, but merely heard a misleading account of it from a person who was fooled by it. This is another general fact about scientific explanation. If one has a misconception, observations that conflict with one's expectations may or may not spur one into making further conjectures. But no amount of observing will correct the misconception until after one has thought of a better idea. In contrast, if one has the right idea, one can explain the phenomenon even if there are large errors in the data. Again, the very term data givens is misleading. Amending the data or rejecting some as erroneous is a frequent concomitant of scientific discovery, and the crucial data cannot even be obtained until theory tells us what to look for and how and why. A new conjuring trick is never totally unrelated to existing tricks. Like a new scientific theory, it is formed by creatively modifying, rearranging, and combining the ideas from existing tricks. It requires pre-existing knowledge of how objects work and how audiences work, as well as how existing tricks work. So where did the earliest conjuring tricks come from? They must have been modifications of ideas that were not originally conjuring tricks. For instance, ideas for hiding objects in earnest. Similarly, where did the first scientific ideas come from? Before there was science, there were rules of thumb and explanatory assumptions and myths. So there was plenty of raw material for criticism, conjecture, and experiment to work with. Before that, there were our inborn assumptions and expectations. We are born with ideas. We are born with ideas and with the ability to make progress by changing them. And there were patterns of cultural behavior, about which I shall say more in chapter 15. But even testable explanatory theories cannot be the crucial ingredient that made the difference between no progress and progress. For they, too, have always been common. Consider, for example, the ancient Greek myth for explaining the annual onset of winter. Long ago, Hades, god of the underworld, kidnapped and raped Persephone, goddess of spring. Then Persephone's mother, Demeter, goddess of the earth and agriculture, negotiated a contract for her daughter's release, which specified that Persephone would marry Hades and eat a magic seed that would compel her to visit him once a year thereafter. Whenever Persephone was away fulfilling this obligation, Demeter became sad and would command the world to become cold and bleak so that nothing could grow. That myth, though comprehensively false, does constitute an explanation of seasons. It is a claim about the reality that brings about our experience of winter. It is also eminently testable. If the cause of winter is Demeter's periodic sadness, then winter must happen everywhere on earth at the same time. Therefore, if the ancient Greeks had known that a warm growing season occurs in Australia at the very moment when, as they believed, Demeter is at her saddest, they could have inferred that there was something wrong with their explanation of seasons. Yet, when myths were altered or superseded by other myths over the course of centuries, the new ones were almost never any closer to the truth. Why? Consider the role that the specific elements of the Persephone myth play in the explanation. For example, the gods provide the power to effect a large-scale phenomenon, Demeter to command the weather, and Hades and his magic seed to command Persephone and hence to effect Demeter. But why those gods and not others? In Nordic mythology, seasons are caused by the changing fortunes of Freyr, the god of spring, in his eternal war with the forces of cold and darkness. Whenever Freyr is winning, the earth is warm. When he is losing, it is cold. That myth accounts for the reasons about as well as the Persephone myth. It is slightly better at explaining the randomness of weather, but worse at explaining the regularity of seasons. Because real words do not ebb and flow so regularly except insofar as that is due to seasons themselves. In the Persephone myth, the role of the marriage contract and the magic seed is to explain that regularity. But why is it specifically a magic seed and not any other kind of magic? Why is it a conjugal visit contract and not some other reason for someone to repeat an action annually? For instance, here is a variant explanation that fits the facts just as well. Persephone was not released. She escaped each year in spring when her powers are at their height. She takes revenge on Hades by raiding the underworld and cooling all the caverns with spring air. The hot air, thus displaced, rises into the human world, causing summer. Demeter celebrates Persephone's revenge and the anniversary of her escape by commanding plants to grow and adorn the earth. This myth accounts for the same observations as the original, and it is testable and in fact refuted by the same observations. Yet what it asserts about reality is markedly different from in many ways. It is the opposite of the original myth. Every other detail of the story, apart from its bare prediction that winter happens once a year, is just as easily variable. So although the myth was created to explain the seasons, it is only superficially adapted to that purpose. When its author was wondering what could possibly make a goddess do something once a year, he did not shout, "Eureka!" It must have been a marriage contract enforced by a magic seed. He made the choice, and all his substantive choices as author for cultural and artistic reasons, and not because of the attributes of Winter at all. He may also have been trying to explain aspects of human nature metaphorically, but here I am concerned with the myth with only in its capacity as an explanation of seasons, and in that respect, even its author could not have denied that the role of all the details could be played equally well by countless other things. So I have just read the pages from 11 to 20. Now I'm going to discuss about what I have learned from reading these 10 pages. So from the pages, so I'm starting from the pages 11 here. So it seems to me that this is discussing the nature of scientific knowledge and the progress of understanding through history. So if I were to summarize this is how I would do it. 1. Understanding complex phenomena. The text starts by questioning how humans can comprehend complex scientific phenomena such as subatomic particle interactions in distant stars or the events during the Big Bang, which are beyond direct human experience or observations. It reflects on the marvel of how science allows us to predict the future or develop technologies, despite having no direct experience with such phenomena before. Right. And 2 would be regarding historical limitations of knowledge. The text explains how, for most of human history, people lacked the ability to understand or explain the world scientifically. They observed the stars, wondered about their nature, and identified patterns, but their knowledge was limited to appearances without a deeper understanding of the underlying realities. The challenge wasn't due to a lack of curiosity, but rather a lack of the necessary intellectual tools and frameworks to make sense of the world. And the third point would be about practical concerns of ancient people. Ancient people were primarily focused on survival, ensuring their food supply, safety, and comfort. Although they occasionally pondered more abstract scientific questions, these took a backseat to immediate practical concerns. The need for scientific understanding in earlier times was driven by survival needs rather than pure curiosity. And the fourth point would be, I think, about scientific revolution and the Enlightenment. The author, David Deutsch, who is, I guess, a British author, he transitions into discussing how the Enlightenment marked a shift in human understanding. Before this period, knowledge was often based on authoritative sources like ancient texts or religious doctrines. Progress was made when thinkers started questioning these authorities and developing a tradition of criticism. So that means in order to make progress in our society today, we need to question, we need to learn how to question authorities and how can we improve in every areas that we are concerned of. And we can develop a tradition of criticism which emphasized rejecting ideas that couldn't withstand scrutiny and focusing on empirical, testable knowledge. And the point 5 would be the testability as the core of scientific progress. The most important change that emerged from the Enlightenment was the idea that scientific theories must be testable, subject to experiments and observations that could potentially disprove them. The example given is how early experiments refuted the belief that transmutation of elements was impossible, leading to groundbreaking discoveries in physics and chemistry. So, the key learnings from these pages would be that so here the author highlights the power of scientific inquiry, emphasizing that progress is made not through authority but through criticism and testable hypotheses. Human understanding of the universe, from subatomic particles to cosmic phenomena, has evolved because of a shift away from relying on authoritative knowledge and toward empirical investigation. The Enlightenment's tradition of skepticism, testability, and rejection of unproven claims laid the foundations for modern science. But when it comes to scientific progress, scientific progress often requires breaking away from long-held assumptions, which is exemplified in the discovery of radioactivity and the transmutation of elements. The later pages, such as page 14 to 18, I think these pages discuss the nature of problems, explanations, and scientific inquiry. So the key points I learned from this are number 1 would be problems arise from conflicting ideas or when existing explanations fail to adequately capture or explain observations. And point 2 would be curiosity stems from recognizing that our current understanding is insufficient, prompting further inquiry. And point 3 would be a problem is defined as a situation where we experience conflicting ideas. And point 4 would be scientific problems are dependent on prior explanatory theories. For example, a conjuring trick is only perceived as impossible because of our existing explanations about how things should work. And point 5 would be solving a problem means creating an explanation that resolves the conflict between existing ideas and observations. Point 6, the perception of problems depends on our background knowledge and expectations. For instance, stars remaining fixed in the sky was only seen as a problem because it conflicted with existing explanations about falling objects and fuel consumption. Point 7, problems can arise purely theoretically without direct observation, such as when a theory makes an unexpected prediction. Point 8, the concept of a problem covers a range of situations from unpleasant like technical issues during space missions to pleasant like intellectual challenges in science. Point 9, explanations are central to scientific progress. Good explanations are hard to bury while still accounting for the phenomenon they describe. And here the author, David Deutsch, emphasizes the importance of creating an and criticizing explanations in the process of scientific discovery and problem solving. So I think here the author has strongly highlighted the interconnected nature of problems, explanations, and scientific progress, emphasizing how our existing knowledge shapes our perception of problems and drives further inquiry. And on the later pages, page 19 and 20, what I learned was that here the author, David Deutsch, discusses the nature of explanations, myths, and scientific progress with more detail. So the key points to learn from here. 1.1 would be the origin of ideas. Both conjuring tricks and scientific ideas evolved from pre-existing knowledge and concepts not originally intended for those purposes. So it seems to me like some ideas occurs accidentally. Like if you go on the street and you walk, you might not necessarily be all the time thinking about your walk, but you can be thinking about something else. And so I think in these situations, or all kinds of situations, serendipity happens, or epiphany or serendipity really does happen. And the point 2 would be pre-scientific explanation. Before formal science, people relied on rules of thumb, assumptions, and myths to explain phenomena. Point 3, innate capacity for progress. Humans are born with ideas and the ability to change them, which is fundamental to making progress. The role of testable theories, while important, testable explanatory theories alone don't account for the difference between progress and lack of progress. And the next point would be myths as explanations. Here the author uses the Greek myth of Persephone to illustrate how myths served as explanations for natural phenomena. In this case, the changing of seasons. There are countless myths that we tell to relate it to our daily activities and even seasons and other natural phenomena. And the next idea would be about the testability of myths. Even though myths are false, they can be testable. The Persephone myth makes predictions that could be falsified by observing different seasonal patterns in other parts of the world. And the next point would be persistence of inaccurate explanations. When myths were replaced over time, the new ones were rarely more accurate. This raises questions about why inaccurate explanations persist. And the next point would be about the comparison of myths. Here the author compares the Greek Persephone myth with a Nordic myth about Freyr to show how different cultures explained the same phenomenon. Next point, variability in myths. So myths really does vary. The author provides a variant of the Persephone myth to demonstrate how easily details can change while still explaining the same observations. So you might be thinking, what is the purpose of myths? While created to explain natural phenomena, myths often incorporate elements for cultural, artistic, or metaphorical reasons rather than purely explanatory ones. And the next point about the page 20 would be And the nature of explanations. So this is like here the author highlights how explanations, even when inaccurate, can be adapted to fit observations, and how specific details in explanations like the magic seed in the Persephone myth, which I read just a few minutes ago, are often arbitrary. So in the end, or in conclusion, I can say, or in summary maybe, the author has illustrated the complexity of human explanations, the evolution of ideas, and the challenges in developing accurate scientific theories. And also he emphasizes the importance of critical thinking and testing explanations against observations. Alright, no more today. So I have read the first 20 pages so far. First 10 pages in one episode, and the next 10 pages from 11 to 20 on this episode. And I'll read the next 20 pages from 21 to 30 on the next episode. So keep listening for learning more. And if you have any comments and want to discuss any particular topic, please write a comment in the description below. No, in the comment box below. And hopefully talk to you soon.